I am Marios Zacharias, Senior R&D Project Manager in Space Hellas, and this MOOC is about data connectors for trusted data exchange. In this MOOC, we will explore and discuss the essential role and implementation of data connectors and their applicability within the PISTIS project. We will begin by discussing what are data connectors and what's their role, providing an introduction to the concept, functionality, and significance of data connectors in modern data-driven ecosystems. Then we will see why we need a data connector in PISTIS. Subsequently, we will dive into the PISTIS Factory Data Connector in terms of architecture, design, and capabilities. Then we will see its interdependencies with other PISTIS components. And finally, we will summarize the key takeaways from this presentation. Now let's see what data connectors are and what is their role. Data connectors are software interfaces that enable the connection, integration, and exchange of data between heterogeneous systems. They're critical for breaking down data silos, allowing information to flow freely and cohesively, thus facilitating seamless data movement. Now, why they're essential? We need them to share data because connectors enable secure and effective communication and exchange, especially in the case of data spaces. Such connectors can be seen as a tool to connect many data endpoints, to increase the pool of available data and accelerate the data economy. Connectors enable data integration. They act as the backbone for integrating diverse systems, allowing them to share and synchronize data seamlessly. They enable data transformation. Many systems have incompatible formats, and connectors address this issue by transforming data into the required structure and format for the destination system. This feature is vital for interoperability. Then they support operational flexibility. Real-time connectors are ideal for scenarios requiring immediate updates such as live dashboards or IoT systems. On the other hand, batch connectors are more suited for periodic tasks like nightly database updates or large-scale data processing. Finally, connectors facilitate user accessibility. By minimizing the need for technical expertise, they make data management tools more inclusive and widely usable. This is particularly important for teams with limited coding experience or resources. Now let's see how data connectors work. First of all, we establish a new connection. The first step involves creating a link between the source, for example, an application or a database, and the destination system, for example, data warehouse or BI tool. Connectors or adapters are used, designed to understand the communication protocols and data formats required by each of the two systems. Then we have data extraction. Once connected, the connectors extract data from the source system. They support two main extraction methods. First, the complete extraction, where all available data is retrieved, and incremental extraction, where only newly added or modified data are fetched, optimizing the process for efficiency. The third step is data transformation. Connectors can include transformation capabilities to reformat or clean the data. Typical tasks include removing inconsistencies in the frame of data cleaning, applying filters to focus on specific datasets, or enriching the data with additional context. In the fourth step, data loading, transformed data is loaded into the destination system, such as a cloud data warehouse. This phase ensures that data is properly formatted, validated, and adheres to integrity checks, preventing errors in the destination system. Finally, the entire process is tracked through logging and monitoring features. If issues arise, connectors can retry failed transfers or notify administrators for immediate action. Some systems trigger also automated solutions to resolve issues, minimizing manual intervention. Now let's see what data connectors are for data spaces. Data connector is the core component of a data space. It plays a crucial role in enabling trusted and secure data sharing between participants, allowing data to flow seamlessly across different systems and devices. The data connector is responsible for establishing secure connections, verifying the identity and authorization of participants, and ensuring data integrity and confidentiality. Additionally, the connector provides an interface for accessing and exchanging data while ensuring data usage control. This mechanism allows data providers to set rules and policies regarding who can access their data and how it can be used or shared. Finally, data usage control helps protect sensitive data from unauthorized access and ensure that data is used only for intended purposes. Effective data usage control is critical for maintaining data sovereignty. Data connectors differ across multiple dimensions, but they can generally be grouped into four main categories. First, frameworks. These are modular data space components used as the foundation for implementing data connectors. Most frameworks are available as free and open source software components. Developers can build solutions by extending these frameworks. The most important examples here include the Eclipse Data Space Connector, the FIWare ecosystem, including the True Connector and the IDS messaging library. These frameworks are designed for developers rather than end users, meaning that they require additional development work to share and consume data. Then we have open source generic solutions. These provide data connectors that can be integrated directly into an IT landscape. They often act as proxies or gateways to an organization's IT service. Configuring the components and adding custom extensions is typically required to share and consume data. The most important examples here include the Data Space Connector and the TNO Secure Gateway. Then we have proprietary generic solutions, which are offered by companies and organizations as a proprietary software for generic usage. Like their open source counterparts, they typically require additional configuration and extension to meet specific needs. An example is the Nikos Gaia box connector. Finally, we have off-the-shelf connectors, which are ready to use either as a service or as a product that can be directly integrated into an IT system with minimal configuration. While some adaptation might be necessary, these solutions significantly reduce the effort required compared to more customized options like the ones mentioned earlier. One example is the connector as a service offered by Sovity. In extension to such data connector offerings, we can also mention the Data Intelligence Hub and the Tech2B connector. The data space connector concept is to act as a secure gateway between parties exchanging data. Support both a data plane, which is the actual data transfer, and the control plane, which includes identity management, access policies, contract negotiation, logging, etc. And finally, to integrate both planes to ensure seamless and secure transactions. An important example of data space connector is the International Data Spaces Connector, which is a central component of the IDS standard. The IDS connector uses container technology to ensure trusted execution, meaning that the data within the container is always protected from unauthorized access. The data space protocol introduced is mandatory for all data connectors to ensure interoperability and is expected to be included in the IDS certification. Now let's see the benefits of using data connectors. First, we have seamless integration across diverse systems. Connectors unify systems, enabling organizations to eliminate data silos. This fosters collaboration and ensures a cohesive view of information, making workflows more efficient. Second benefit is the real-time data synchronization. Real-time updates ensure that as data changes in one system, it is immediately synchronized across others. It's critical for time-sensitive scenarios like e-commerce, which include tasks like inventory updates, finance, and supply chain. Third benefit is about enhanced analytics and business intelligence. By enabling access to various data sources, connectors support the creation of dashboards and reports. This improves decision-making by providing actionable insights based on historical and live data. Automation and workflow efficiencies. Data connectors automate data integration tasks, reducing reliance on manual processes. This saves time, streamlines operations, and enhances efficiencies. Data-driven decision-making. By ensuring centralized and accurate data, connectors empower stakeholders to make well-informed decisions. This capability enhances competitiveness, customer satisfaction, and enables the completion of overall strategic goals. Scalability and flexibility. As businesses grow or evolve, connectors can adapt to new data sources and systems, ensuring that businesses remain agile and responsive to market demands. Now let's see why we need a data connector in PISTIS, along with the relevant methods and technologies we have used. The PISTIS data connector enables peer-to-peer data transfer. P2P methods, once dominant before the cloud era, are regaining popularity due to privacy and security concerns with centralized data sharing. P2P methods ensure trusted, secure, end-to-end data transfer without intermediaries or third-party infrastructures. It also supports both synchronous and asynchronous communication for bulk or real-time data exchange using various protocols and tools. In the framework of PISTIS, P2P data transfer is characterized by these elements. First, data transfer is the final step in a monetary or contractual agreement where the agreed dataset is delivered to the buyer after an electronic contract is in place. Direct data exchange between PISTIS Data Factory deployments ensure a secure private connection without any intermediaries. Speaking of which, the absence of intermediaries ensures that stakeholders retain complete control over their data throughout the entire process. Finally, this controlled direct method is crucial to support PISTIS global services like lineage tracking and transaction monitoring, as these rely on the secure internal transfer methods unique to the PISTIS deployment. Direct transfer occurs exclusively between data factory deployments, restricting external access and enhancing security guarantees. There is a number of available peer-to-peer data transfer methods and technologies. Data transfer through RESTful APIs. REST APIs are one of the most widely used methods for exchanging data between systems. They operate on standard HTTP methods like GET and POST. These methods are predefined and documented so that both data provider and consumer understand how to interact. REST APIs interact with backend systems like databases to fetch or store data. Security features such as encryption through HTTPS and authentication tokens like OAuth, JWT, and API keys ensure safe and controlled access. This approach enables seamless integration between applications while maintaining security and reliability. Then we have event and data streaming platforms. When dealing with real-time or continuous data streams, REST APIs may not be the best solution. Event streaming platforms like Apache Kafka or Apache Pulsar allow data producers to send data continuously while consumers subscribe to receive updates as they arrive. PubSub servers follow a similar approach where data producers publish events and subscribers retrieve only the relevant data. Message brokers like RabbitMQ or ActiveMQ are useful for managing communication between microservices, but are not optimized for transferring large-scale streaming data. Streaming solutions are particularly useful in high-throughput environments like IoT, financial transactions, and real-time analytics. The third point is about data exchange between data spaces participants. Traditional data exchange methods do not fully address data sovereignty and security challenges in data spaces. Data space connectors are introduced to provide a secure gateway for data transactions between participants. The IDS data space connector, which follows the relevant IDS reference architecture model, is one of the most important examples. The connector operates on two planes. First, the data plane that ensures the actual transfer of data between entities, and the control plane that handles governance aspects such as identity management, access control, contract negotiations, and logging. Overall, this approach enhances trust, transparency, and security in data sharing ecosystems. Finally, we have file transfer protocol connections. FTP is a traditional method for transferring files between parties using an FTP server. It is still used for cases requiring large file transfers, such as datasets that are too big for standard API-based exchange. However, FTP is not ideal for modern data ecosystems due to several drawbacks that have to do with limited integration capabilities and lack of security measures, unless FTPS or SFTP protocols are used. Moreover, they have limited governance, since access control and monitoring capabilities are weaker compared to the other solutions. Now let's see the PISTIS Data Factory Connector. The overall data transfer in PISTIS is facilitated by the PISTIS Data Factory Connector, or the PISTIS connector, which is an infrastructure that is tasked once a data transfer contract needs to be executed to fetch the data stored in the PISTIS Data Factory of the data provider and pass it to the PISTIS Data Factory of the data consumer. This transfer is to be performed following the appropriate checks at smart contract level that will govern such exchanges based on license, usage, and permission attributes stored in the blockchain. The result will be the deposition of the data asset purchased by the data consumer in his own local data storage. The main technology used for the component is Node.js, based on the Nest framework, as the whole component is a backend service deployed at the side of each PISTIS data factory. And it can ingest and provide data to other deployments as instructed by the smart contracts. Now let's delve into the internal architecture of the PISTIS Data Factory Connector. Its main elements begin with the smart contract checker, which is used to retrieve and analyze the details of the smart contract to resolve how the system shall proceed with the transfer. Then we have the transfer gateway registry, which is used to store transaction-related data locally in order to support certain operations, such as transferring data in batches and so on. Then the Data Factory Storage (I/O) service is retrieving the data stored in the local storage of a PISTIS Data Factory so that its transfer is concluded. The same component also writes back to the PISTIS Data Factory of the data consumer once he has acquired the data asset. Then the metadata repository I/O service is retrieving the assets metadata stored in the PISTIS Data Factory storage to transfer it. The same component also writes back the assets metadata to the metadata repository of the data consumer once has acquired the data asset. Then we have the request data reception service. This is used to request and receive specific data asset based on an active smart contract along with the relevant information. Then we have the data publishing service, which is used to bundle the data and the metadata of an asset. Then it sends to the request data reception service of the PISTIS Data Factory Connector component that resides at the side of the data consumer. The PISTIS Data Factory Connector is designed to facilitate secure, automated, and transparent data exchange between data providers and consumers. Its key features include automatic data transfer, ensuring that datasets or slices of them are seamlessly delivered to the data consumer. Blockchain-based logging, providing evidence for all transfers and enabling traceability. An upcoming notification system which will alert users of successful transfers or provide error codes for failed ones. Smart contract integration that ensures compliance with licensing and permissions before the transfer is executed. Finally, another future capability includes automatic subscription-based updates, enhancing trust, transparency, and usability within the PISTIS ecosystem. Now it is time to see the interdependencies of the PISTIS Data Factory Connector with other PISTIS modules. The most important interaction of the PISTIS connector is with the data exchange bundle. P2P exchange of data asset between a data provider and a data consumer is facilitated by the data exchange bundle, ensuring adherence to the terms of the contract that has been signed to govern the overall transaction. This bundle consists of two key components: the data factory connector that executes data transfer processes, and the smart contract checker that ensures the integrity and compliance of smart contracts within the PISTIS ecosystem. In PISTIS, peer-to-peer exchange Now let's focus on the smart contract checker component. This ensures the integrity and compliance of smart contracts within the PISTIS ecosystem. It's an integral component of the PISTIS platform, instilling confidence in the PISTIS transactions. By rigorously validating user authenticity and transaction logic, it upholds the platform security and compliance standards. This comprehensive approach to transaction violation ensures that PISTIS remains a secure, trustworthy, and user-compliant platform that is capable of handling complex data and financial transactions with utmost integrity. The Smart Contract Checker tool is designed to validate the integrity and compliance of smart contracts through a two-step analysis process. It begins with the authenticity check module that verifies the originality and correctness of the contract vis-à-vis predefined standards. Following this, the violations check module scans for any breaches of contractual or regulatory rules embedded within the contract logic. The results from these modules are compiled into the Smart Contract Checker result, which details the status of the contract in terms of authenticity and legal compliance. This systematic approach helps ensure that smart contracts are both genuine and adhere to all applicable laws and regulations. The PISTIS Data Factory Connector interacts with several PISTIS components to facilitate secure and efficient data transfers. As we can see in this slide, inputs flow into the gateway from components like the Smart Contract Execution Engine when it comes to transaction details, PISTIS Data Storage that deals with data payload, Factory Data Catalog in terms of metadata of the asset, and Data Factories Registry when it comes to the factory address. On the other hand, outputs are sent to respective components, ensuring transaction results, transferred data, and metadata are securely stored and managed. Overall, this architecture supports interoperability and ensures data sovereignty in the PISTIS ecosystem. Now, concluding this MOOC, let's see the key takeaways from this presentation. Data connectors are foundational in enabling interoperability between heterogeneous systems by providing secure and effective communication. By connecting multiple data endpoints, they eliminate data silos, enabling better insights and decision-making. They improve operational efficiency by automating data transfers and scaling to meet growing data demands. Finally, their role extends beyond technical integration as they ensure compliance with data sovereignty and security standards that are crucial for sensitive or proprietary data sharing. In the case of data spaces, data connectors are considered as their backbone since they can ensure data sovereignty, security, and interoperability in data spaces. They enforce trustworthy data exchange through access controls, identity verification, and policy enforcement. Moreover, they can incorporate technologies like distributed ledgers for added security and compliance. The PISTIS Data Factory Connector serves as a core component in the PISTIS ecosystem, ensuring smooth execution of data contracts by automating data transfers between data providers and consumers. Security is a primary focus, with the connector verifying permissions, licenses, and other compliance requirements through blockchain-backed logs. Its ability to streamline P2P data exchange reduces reliance on intermediaries, offering direct control to stakeholders over their data. It operates as a backend service, integrating with other PISTIS modules, including smart contract verification. In the upcoming releases of the PISTIS platform, the new features will include notifications for successful transfers and updates for subscription-based datasets, demonstrating its future scalability and user-centric design. Concluding, the overall benefits of a dedicated data connector in PISTIS have to do with trust and security, ensuring secure data handling and policy enforcement. When it comes to efficiency, it automates data ingestion, transformation, and transfer, reducing manual effort. Scalability is also promoted by adapting to increasing data volumes and evolving business needs. Finally, the PISTIS connector fosters interoperability by simplifying integration with internal and external systems. This was a PISTIS MOOC about data connectors for trusted data exchange. Thank you very much for your attention.